This is the fourth section of chapter 2, which is centers of mass of plane figures, and this section is about how we can find the center of mass of a composite lamina. So first of all, just like composite shapes, a composite lamina can be split up into different shapes. So here are some examples. So here we've got something where we can split it up into a rectangle and a semicircle. The second one, we can split that up into a rectangle and a triangle at the top. And even a third one, where we've got a circle with this square hole in the middle, it can still be split up into a circle and a square with this hole in the center of it. Now, with some laminas, there may be more than one way of splitting them up. So, for example, let's say I had a lamina that looked like this, for example, I could split it up this way. Okay, and get to like a rectangle and a square there. That's one way of doing it. I could instead split it up this way. Yeah, so here I'd have two rectangles. Or a different way of thinking of this is actually to think of it as a larger rectangle like this with this section cut away, this section up here, just leaving like this. So yeah, a third way of thinking of it is that we've got this larger rectangle that includes the dotted lines with this section cut away or subtracted from the total area. Now when we split up a shape, we must split it up into one of these shapes here, a circle or rectangle, triangles or sectors, because we learnt about these shapes in the last section and how to find the mass of these four different types of shape. So let's now go through the method to find the center of mass of a composite lamina. So we've divided our lamina up into parts. And what we need to do is to find the area of each part. And this area we're going to be using for the mass in this formula here, the sum of mx over the sum of m. So m is going to be the area of a part. Next, we're going to find the center of mass of each part. So if it was something like this, I'd find the center of mass of this rectangle and then the center of mass of this semicircle. And we can use symmetry here. So for example, on this shape here, the rectangle with the semicircle on the top, because this is a line of symmetry, I know the center of mass in the x direction is going to be on this line. So I don't need to work out x bar, I only need to work out y bar. So any shape where we've got symmetry, so for example, this shape here, well, since the square is in the center, not really a helpful example, but then the center of mass would be at the center. So actually what might be more helpful is maybe to move that square off center like that. So there's a hole there. And let's say then we've got something like this as our question, then it may not have a line of symmetry again. That's not a great example. Let's move that square so that it's here. Let's say that square is halfway up. So I've got something here that's a bit more useful. So imagine that this is halfway up along the diameter there. The center of the square is along the diameter of the circle going horizontally this way. Then I can use symmetry to find the center of mass. Now in this case, I know the center of mass is going to be along this line of symmetry here. So I don't need to work out y bar because I'll know that it'll be whatever this value is here, this y value. I only need to work out x bar, which is how far across that center of mass is. So symmetry is often helpful. We don't need to do a calculation. We can just look at what the coordinates are and use that to help us work out the center of mass. And then we just do the same calculation we do before. So we do sum of mx over the sum of m, where m is the area and x is the center of mass of a part. So basically this formula now becomes area times center of mass for each part, and we find the sum of those and we divide by the sum of the areas. Now some shapes have holes in, like this one. So the only difference is that when we work out mx, we subtract it, and we work out m, we subtract it. So it's still the sum, but you could think of mx and m as being negatives in that sum. And then lastly, we might want to organize our results because we might have lots of working to do. So I found it helpful to put it in a table like this, where maybe I'd put the shape and actually draw the shape in this part, including like the holes, maybe bits that I need to subtract. The area of that shape in this column, its center of mass in the x direction in this column, and the center of mass in the y direction in this column, and then I can easily work out the center of mass of this whole composite lamina quite easily by multiplying and adding bits in the table. And actually, if I've got holes, I could actually put down negatives next to my working so that I don't forget to do those negatives when I do the sum of mx over the sum of m. Example 11. A uniform lamina consists of a rectangle PQRS, here we go, PQRS, joined to an isosceles triangle QRT, as shown in diagram, so they've marked on that these two sides are the same length here. Find the distance of the center of the mass of the lamina from PQ and PS. Now, since we're finding the distance of the lamina from those points, it makes sense to put the origin here. So the first thing we're going to do is to draw a diagram and then put the origin where point P is. Okay, so here's my sketch. I've actually drawn it so that 1 square is 1 centimeter, but you don't need to do that. What's important is that you have the correct numbers on the scale. Okay, so the first thing that I notice is that if I want to find the center of mass, this is actually symmetrical about this line here, y equals 2. So let me draw that line of symmetry in, and I can use that to find y bar, which is the center of mass in the y direction. So that is actually the distance of the center of mass from the line PQ, because PQ is on the x-axis. So I can write for part A that by symmetry, so I don't even need to do any working, the distance of the center of mass from PQ, the distance of the center of mass from PQ is 2. So now that's all that's left to do is to work out how far along this dotted line the center of mass is. Now, when you do these types of questions, it's useful to think, well, roughly where would I expect it to be? Would I expect it to be sort of towards the left hand side, towards the right hand side? Well, without the triangle, it would be somewhere towards the center of the lamina here, the center of that rectangle. But obviously this triangle is going to add something to the center of mass, so I expect it to shift a little bit further on from the center. Now, I don't expect it to be right at the edge of the rectangle shape here at the bottom of the triangle or in the triangle shape. So I'm expecting to be a little bit further across than the center. Always look at your answer and think, does this make sense? So in part B now, we're going to work out x bar. So this is where we're going to use a table and split the shape up. So I can see it's going to make sense to split the shape up along here, that green line there. Okay, so here's my table and I'm ready to fill it in. So I've got my shapes here. I'm going to work out the area, the center of mass in the x direction. Now I've put this column in here. I don't need it because I know by symmetry what the center of mass of the total lamina is in the y direction, so I don't need to do that calculation. But I will put these values in and I will work out the center of mass manually just to confirm that I do get the same answer just by using symmetry. So we'll start with the rectangle shape, and that area is going to be 8 times 4, so that gives me an area of 32. And we'll work out the area of the triangle here, so we'll just do half base times height. The base is 4, the height is 3, so half base, so that was 4 times by 3, so that's going to be an area of 6. Now we can use the standard rule for a rectangle to find its center of mass. Okay, and that would be where the two lines of symmetry cross, so we'll just put that in there. And I can see, I don't really need to draw that in, that it would be in the x direction 4 and in the y direction 2. So we'll just put those values in. 4 in the x direction, 2 in the y direction. So now we want to find the center of mass of the triangle in the x and y direction. Well, we know in the y direction it's 2, so we can put that in. And there's actually two ways that we can find the center of mass of this triangle in the x direction. So how far along this line is the center of mass? It's going to be along that line of symmetry. We can get all the x coordinates here, add them together and divide by 3. So that's method number 1. So if I do it that way, if I do 8 plus 8 plus 11, so add together all the x coordinates and divide by 3, that'll give me 16. 27 divided by 3, so that'll give me 9. Okay, now there is another way that we can find it. Now remember that when we've got these medians here, or in this particular case the isosceles triangle, this line of symmetry, that the center of mass is 1/3 along the length of this line from the midpoint end. So the center of mass is going to be 1/3 of this length from here to this end. Or if we've got the pointed end and we've got that median going along, or line of symmetry, then it's 2/3. So if I know the length of this end here, I can then take away 2/3 of that to find out what this is here. Now this is quite easy because the distance between the 8 and 11 is 3, so it's 3 units from there to there. So the center of mass is going to be 1/3 along. It's going to be 1 unit along from the 9, so from the 8. So it's going to be at 9. That's 1/3 along this line of length 3. So that's another way of doing it. It's probably a little bit quicker. So again, I get the center of mass as 9. Now in the same way, I could work out what the y coordinate of the center of mass is. Now obviously it's easier by symmetry, but if I were to add together the y coordinates of the vertices of this triangle and divide by 3, I should get the same answer. And if I to do that, then the y coordinates are 0 for q, y coordinate of 2 for t, and a y coordinate of 4 for r. Divide by 3, 6 divided by 3, you get 2, so we get the same answer if we do it that way. Okay, so now let's use all this information to find the center of mass, and I've sort of just added this alternative way of working out the center of mass of the triangle. So x coordinate of 8 plus 1/3 of this length of 3, which also gives us 9. So when in part B we're finding this distance from PS, which is x bar, and x bar is going to be the sum of each area which we're using as the mass, because the area is going to be proportional to the mass since these are uniform lamina. So each mass times by its center of mass in the x direction. So I'm going to have 32 times by 4, there's my first mx, plus my second mx, which is going to be 6 times by 9. So basically the area of each part of the lamina times by its center of mass divided by the total mass, which is the total area, which is 32 plus 6. So we get 182 divided by 38, which simplifies down to 91 over 19. Now if we press the SD button, we get some long decimal, so we'll leave it in that form. So the distance from PS is going to be 91 over 19. Now these are all centimeters, aren't they? So I should put centimeters here, and I'll just highlight those. So we can combine these and then write down what the center of mass of the whole lamina is as a coordinate, which I'll do now. So as a coordinate, the center of mass of the whole lamina is going to be 2 centimeters, comma 91 over 19. Actually the other way around, isn't it? Because we want x bar first and then y bar second. So yes, 91 over 19 centimeters and 2 centimeters. So there we go. Now I did say that we should check to see if our answer is sensible. If we work out what 91 over 19 is, it's about 4.79 to 3 significant figures. So 4.79 is a bit further across from 4, so it's not quite so 5, and that sort of makes sense. this triangle dragging the center of mass slightly across to about here. So that seems like a sensible answer to me. Example 12. The diagram shows a uniform lamina. Okay, got a uniform lamina here. Find the distance of the center mass of the lamina from AF and AB. So let's just highlight those two sides, AF and AB. So those two highlighted sides should be on my axis. I'm placing the origin at A, so I'll just do a sketch of that. Okay, so here's my lamina drawn, and I've put like the coordinates on. So since I know this length is 6, that has to be a coordinate of 2, and that's 2 going up, so I've put that 2. So it's important that we put these numbers on the axis. So now I need to split this up. So there are 2 ways I can split it up. I can either split it up and draw a dotted line here and find the center of mass of the square and rectangle, or I can split it up here. It's totally up to you. For some reason, to me, it just seems that I want to split it up that way. But as I said, it doesn't really matter. Either way, you'll get the same answer. So now I'm going to find the center of mass of each of these, and I can do that by symmetry. So for this part of the rectangle, it's going to have a center of mass there. I can write that coordinate down. And for this part of the rectangle, it's going to have a center of mass there. So if I were to call this G1, for example, that is 1, 2. And for this one here, if I call this G2, then that center of mass, I need to make sure I've got the coordinates right, halfway between 2 and 8 is going to be 5. Now I've done it where I've drawn 1 square per unit, but if you haven't, just make sure you use the numbers that you've got on your coordinate grid to find the midpoint. And then the center of mass of this rectangle in the y direction is just going to be halfway between 1 and 0 and 2. So that's going to be 1. So I've got the center of the mass of the 2 parts of this composite lamina. So I'm now going to take that information and put it into a table. Okay, so here are my 2 shapes. So this first shape here is this rectangle here. So I want its area, so that's just going to be 2 times 4. So I have an area of 8. And I'll do the same for this rectangle here. This is going to be 6 times 2, so that's got an area of 12. And 2 equals 12. And now I'm going to write down the x and the y coordinate of the center of mass for each one. So for this shape here, it's 1 and 2. And for this shape here, it's 5 and 1. So now we're ready to answer part A. And if I'm finding the distance of center of mass of the lamina from AF, so that's this side here, I want to find how far along it is. So that's finding x bar. So distance from AF equals x bar. So that's the sum of mx. So remember the area is the mass here, divided by the sum of the areas, the sum of the masses. So that's going to be, starting with this one here, 8 times 1, in black, 8 times 1, plus 12 times 5, over the sum of the masses, which is going to be 8 plus 12. So that's 68 over 20. So that's 3.4. That's going to be centimeters. And in part B, the distance from AB here, so that's going to be how far up it is. So that's going to be y bar. So mass times its center of mass in the y direction, plus the second mass times its center of mass in the y direction, divided by the sum of the masses. That leaves me with 28 over 20, which is going to be 1.4 centimeters. So again, if I wanted to write down the coordinate of the center of mass, it would be 3.4 across, so it'd be about that much across, 1.4 up, so it'll be about here, which seems about right. I would be suspicious if the center of mass was, right in a corner here. It's going to be somewhere towards the center. this shape here is giving more towards the center of mass than this one, because obviously it's a bigger area. So yeah, it seems about right for it to be roughly in this type of position. Now, an alternative method to doing this question would be to treat it as a larger rectangle like this and find the center of mass of this whole rectangle, 32. Then find the center of mass of this larger rectangle, which would be 42, and then subtract from it the area and center of mass of this rectangle here. So this rectangle would have an area of 12, 6 times 2, and its center of mass, again, we can do that by symmetry. So it would be 3 across from here. Okay, so actually that would be 5, and then going up, this would be, let's see, 2 here, so it'd be 3, so it'd be 5, 3, and we would subtract the area and the center of mass from the bigger one. We'll get exactly the same answer. Example 13. A uniform circular disc, center O, of radius 5 centimeters, has 2 circular holes cut in it. So as soon as I see holes, I'm thinking about doing a minus in my calculation for mass and mass times center of mass, as shown in the diagram. So diagram here, they've put the center of the circle on the origin there, so that's helpful. The larger hole has radius 2. Okay, so maybe we'll mark that in, that this radius here is 2 centimeters from there to there. And the smaller hole has radius 1, so that's 1 centimeter there. And I think the larger one, they said, had a radius of 5, so we'll just stick that in, 5 centimeters for that radius. And it gives us the coordinates of the center of the holes. So 0, 2, which is that one there, and 2, minus 2 respectively. Find the coordinates of the center of mass of the remaining lamina. So we'll start with a table, and you can see in the first column I've drawn what the shapes are, and because I've got holes, I've put a minus here to remind me that I need to subtract these holes here. So we'll start with the whole circle here, and that's area. We'll leave it in terms of pi, and that will be pi r squared, so pi times by 5 squared, so that's going to be 25 pi. And then the area of this circle here, that's going to be pi times 2 squared times 2 squared, so we have 4 pi. And then a very small circle, which is also going to be subtracted, that's going to be 1 centimeter, so pi times 1 squared, so that's just 1 pi, or just pi. Now we can use the standard results for circles, which means that the center of mass is at the center of the circle. So for the large circle here, its center of mass is going to be at 0, 0, so coordinate 0, 0. For the larger of the two holes, its center of mass is going to be at the center, and we're told the center, so its coordinate is 0, 2, so we can just put that in, 0, 2. And for the small of the two circles, its center of mass is at 2, minus 2, so we'll put that in 2, minus 2. So we'll start first of all by finding the center of mass in the x direction, x bar. So we're going to do the mass on the large circle times its center of mass, 0. Now we need to minus, and we always minus any holes, the 4 pi times by its center of mass, which is circle 0, and also minus the center of mass of the smaller circle, so it's mass times by its center of mass, which is 2. And we divide by the sum of the masses, so 25 pi, but we subtract the holes, minus 4 pi minus pi. And that gives us minus 1 over 10, which we can write as 0, 0.1. So we have the x coordinate of the center of mass. So we'll now do the same for the y coordinate of the center of mass. So now we just multiply these areas by the center of mass in the y direction. So we've got 25 pi times 0 plus 4 pi times by 2, sorry, not plus, minus, and then minus pi times by negative 2, all divided by 25 pi minus 4 pi minus pi, and that becomes minus 3 over 10, which is negative 0.3. So the coordinates of the center of mass is going to be x bar, y bar, which is going to be negative 0.1, comma, negative 0.3. So we'll have a look at that on the diagram, see if that makes sense. So we're saying negative 0.1, so across this way a bit, minus 0.3 down a bit, which sort of makes sense because these are subtracting from the center of mass. We expect it to move away from the center, so it's going to move away from this hole. Okay, so it's going to move down, and it's also going to move away from this hole, so it moves across a bit. So it does make sense for the center of mass to be over here, because these are taking away from the mass and taking away from the center of mass. So that seems like a sensible answer. So you should now be able to do exercise 2D on pages 51 to 54 of the textbook, and there's just like a little recap here.